Hi, my name is Jean Lapierre, Senior Director of Advanced Technology for Matrox. I'm also one of the co-chair for the IPMX activity group at VSF, where we write the specs for IPMX. So as you've heard, IPMX can work without PTP, but it also can work and use PTP. And so today we're going to talk a little bit about how IPMX uses PTP and how it's similar to 2110 and AS67, which require PTP to operate. So we'll talk about the general concept of this protocol. I'm not a PTP expert, okay? I just thought I get lots of questions about it, and so I'm going to explain it to you at a fairly high level, and just so that we understand that PTP, I think, gets a bad rap. It's not that complicated. We could use it on very small network or very big network. What's interesting is that the way IPMX extract timing from the PTP and what we generally do in ProAV with PTP is relatively easy, and therefore, anyway, so let's go over it. We'll look also how the timestamping works in IPMX versus 2110. Okay, so Precision Time Protocol, it's a spec from the IEEE 1588, and there's a specification in SMPTE called 2059. It's actually a specification that explains the profile to use, the 1588 profile to use for 2110. And so PTP is a protocol for sharing clock. A leader clock shares its time with the follower clocks. So when there's more than one leader on the network, there's a best master clock algorithm that's used to pick the best leader. And because there's always, for one domain, only one leader. We'll call him the grandmaster or the GM. Okay, so the grandmaster sends periodic time messages to the network, and followers use these messages to synchronize their clock to the master clock. Excuse me. So there's profiles. So profiles define a valid range of parameters and default value. And AS67 has default parameters as follow. They use a default domain of 0. They have log announce interval of 1. The announce receive timeout is 3. The log sync interval is -3. And the log min delay request interval is 0. You'll notice some of the parameters say log. Why do they say log? Because these parameters are power of 2. I don't know why they did that, but when they say the value is 1, but the parameter is log, like log announce interval value 1, it means 2 to the power 1, which is 2. So it means 2 seconds, okay? I don't know why they just put 2 seconds, but that's what they did. So SMPTE 2110 and IPMX use default parameters for their profile, which is the domain 127, the log announce interval is 0, the announce receive timeout is 3, the log sync interval is -3, and SMPTE uses -3 for the delay request interval, IPMX uses 2. All right. You'll notice that in parentheses next to all these numbers, I put parentheses, let's say for domain says 0 to 127. That means this is the allowed range for that profile, okay? And you'll notice that for some of these parameters, the allowed range for AS67 are different than the allowed range for SMPTE 2110, okay? So we have IPMX, SMPTE 2059, and AS67 that specify these different valid range, but there's an overlap for all these parameters for these range. And so if we're using the values on our network to use these parameters and we set them to the overlap, that means we can use AS67 device with SMPTE, okay, devices and with IPMX devices. Because that means they can operate within that profile. That's the overlap. Excuse me. So these are the messages that we'll talk about. There are other messages part of the protocol, but we'll look at announce, sync, follow-up, delay request, and delay response. So this is an announce message. This is the content of his announce message. We can see that there's a domain number in there. There's clock identity. There's priorities. There's grandmaster class, there's a clock class, the clock accuracy, and other information, okay? We'll go back to what that's used for. So announce messages are used for a few things, okay? If I'm a follower, I use it to discover if there's a leader for the domain I'm following, okay? So I look for an announce message from domain 127, I find one, that's my leader, I start operating. The leaders, they use it to discover if there's more than one leader on the network for the domain that they're doing. And if they do, they look inside the announce message and they look at the parameters and they use it with the busmaster clock algorithm to determine who will be the grandmaster. The busmaster clock algorithm, simplified a little bit. So we have, let's say I'm a leader, okay? So I'm looking to see if there's other leaders on the network. I look at the announce message, I see the same domain as me. So if I find one or more of them, I check if they're better than me, and it's based on parameters inside the announce message, like the priority. Priority 1 is the first thing we look at, and if it's better than me, I just stop and say, okay, you can be the leader, I'll just be quiet. And they look at the clock class and accuracy and everything. And so if they're better than me, I just let them be the grandmaster, okay? Now, if you notice, this algorithm means that the leaders do not have to talk to each other. It's not like I'm a leader, you're a leader, we discuss it, okay, you're better, I'll let you work. Because all I have to do is look at your announce message, and by looking at it, I go, oh, I'm not the best guy, so I'll let you be. So there's no need, it's all based on the announce message content. So it's pretty simple. So, sync messages. So the leader needs to send sync messages containing the time that it was sent on the network. The problem is, with some implementation, especially in software, you have the software that creates the packet for the sync message, and it sends it through a network stack. Okay? And going through that network stack is kind of like not deterministic. It might be a little slow, sometimes a little bit faster, so it's variable time. So it's really hard at the moment that you send your sync message to the stack to know exactly what time that packet will be sent on the network. Fortunately, network card can usually tell you that. And so there's two methods that are used in PTP. One we call one-step, two-step. So what two-step is I send my sync message, and I don't put what time that sync message is sent. I just send it, I quickly read what time it was sent at, and I send a follow-up message that actually contains the time. So now you have a sync message, and the follow-up says, by the way, that sync message was sent at that time. Okay? We solve the problem that way. If it's a system that's able to accurately figure out what time it is when they send the message, then we can do one step where all we get is a sync message that actually has the time accurately that says when it came out, and there's no follow-up message. So one step, just the sync, two steps, sync and follow-up. All right, so network delays and clock synchronization. So we're going to start with a follower that think it's 9 o'clock, 10 seconds, okay? But it's really 9 o'clock. So we have the leader that sends a sync message that says it's 9 o'clock. The network is really slow. The receiver receives it. I've been through the network, and it took 1 second for it to get to me. Okay, so I'm getting a message that says it's 9 o'clock, but it's really 9:01, right? Because of delay. So how do we solve that? So to be accurate, the follower needs to understand what the latency of the network is and compensate for it. And we use delay request and delay response message to fix that. Roughly how that works is the follower, after he receives the sync message and the follow-up, he sends a delay request message to the leader. It says, here's a delay request, and then the leader answers that delay request with the delay response, and it says, I receive your delay request at this time. It sends it back. Okay, and the follower uses all that information to figure out how that works. So let's look at what that means. So we have a little graph here. I have my leader on one side, I have my follower on the other side. At the very top, on the leader side, it says 9 o'clock. On the follower side, it says 9 o'clock and 10 seconds. Okay, so my follower thinks it's 9 o'clock, 10 seconds. Okay, he's later than me, than the actual leader. The leader sends the first message. It's the sync message. Okay, he sends it at T1, 9 o'clock. So T1 is 9 o'clock. The receiver receives the message at its local time, right? He receives it at 9 o'clock, 11 seconds. He receives the message that says it's 9 o'clock. Okay. So he sends a delay request at 9 o'clock and 12. He sends a delay request, says, hey, tell me when you get this. The Grandmaster receives that at T4, and for the Grandmaster, it's 9 o'clock and 3 seconds. And he sends it back. Okay? So now the follower has T1, 9 o'clock. That's when the sync message was sent from the Grandmaster. He has T2, which is 9 o'clock, 11, which is when he received it. He has T3 when he asked for the delay request. And then T4, which is the Grandmaster saying, I received that time. I didn't come up with those formula, but once we put the number in, it's magic. Okay, so we're going to put in the number for T1, T2, T3, and T4 in the equation for the delay. Okay, so I removed the 9 o'clock. I'm just using the 11 second. So T2 minus T1, that's 11 minus 0, plus T4 minus T3, that's 3 minus 12. Oh, complicated math there. That's a negative number. I need to divide that by 2. I do the math, I get 1. Okay, so this equation is telling us the delay through the network is 1 second. Now, I need to check what's my offset so I can adjust my clock. Okay, so again, T2 minus T1, this time minus T4 minus T3 divided by 2. I do the math, it says 10. Hey, it's correct, it works. Okay, so this is how the follower figures out if it's in phase or not, adjust its time, okay? Because if I just took the sync time, it would have adjusted itself to 9 o'clock, yet it was 9:02. It would have been closer than 9 o'clock, 11 seconds, but this works out. Okay. Sometimes we use about transparent clock. We hear about transparent clock and boundary clock. So what a transparent clock is think of the network switch that can accurately measure how long it takes for the packet to come in before it comes out. Okay, so the transparent clock knows about PTP, and it takes the PTP message and says, oh, by the way, I delayed your packet by this amount of time. Okay, so that's what a transparent clock does, and the follower can use that information to more accurately calculate and the delay through the network. Boundary clocks, okay? So let's look at what the problem that boundary clock tried to deal with, okay? So we have PTP traffic on the network. PTP is multicast traffic. Everything gets sent to a multicast address that's over here. All the followers are seeing this traffic, and obviously also is the Grandmaster. As we saw, the Grandmaster needs to reply to each delay request. So if you have a large amount of follower, and they're all asking, can you measure the delay request? The delay will tell me when you get it. The Grandmaster can get pretty busy and stacks up the requests and answers. And by the time he answers when he actually got this packet, like sometimes has passed, so it makes things more complicated. And by the way, all these responses and requests being multicast, all the followers are seeing that traffic. So I'm increasing the traffic on my network. I'm increasing the traffic my followers are seeing. It's just on a big system that can become a problem. So the solution, the switch with a boundary clock implementation. What is that? Well, what it does is it creates a barrier between the Grandmaster and the followers. That's why we call it a boundary clock, right? So the boundary switch, what it does is it follows the Grandmaster. Okay? And it figures out what time it is by talking to the Grandmaster. But it turns around and it becomes the leader for all the devices that are attached to the switch. So it's talking to the device, telling them and doing the Grandmaster's job, but it's really the Grandmaster only sees, so if I have one switch attached to my Grandmaster doing this, the Grandmaster sees one switch. It talks to one follower. It doesn't have to do a lot of work. And my switch is talking to the devices that are attached to it. There's not a million devices attached to a switch, so it has a certain amount to deal with. So this would be a network where there's 128 followers talking to a grandmaster. Normally a grandmaster doesn't have a hard time doing this, but the page wasn't big enough for me to make a very big drawing, so I decided to do this. We have 8 switches, and on each switches there's like 16 devices attached, I think, and that's 128 followers the grandmaster deals with. If I put all these switches in boundary clock mode, I now have 8 followers, the 8 switches that the grandmaster has to deal with instead of 128, and each switch is dealing with 16 followers. So you can see it reduces the traffic, makes things easier for the grandmaster. So on a large network, this is, why we talk about these boundary switches. Okay, PTP and how it's used by 2110 AS67. So the PTP clock is actually not the time of day. It's actually a counter. It's a counter that started at 0 at epoch, and we set epoch to January 1970. And when the clock was 0, it means it was the 1st of January, midnight 1970. Okay? And then it starts to count. And it counts a very accurate count in nanoseconds. So for SMPTE 2110, they defined that all video frames started at epoch. François told us, you think of all the frames, they start at 0 and they start counting. So I'm using a 50 Hertz signal for this example because it makes numbers that are easy to deal with. So imagine you have a 50 Hertz signal that started at epoch. That means every 20 milliseconds there's a frame, okay? And it started then, and it's just counted since then. So I took the PTP clock of March 20th, 2025, 10:37, 13 a.m. Happens to be the time it was when I wrote this. I started writing this document, right? So if you take that clock value, that PTP clock value, and you divide it by 20 milliseconds, we now found out that it's been this amount of frame of 50 Hertz since the beginning of, since 1970, the epoch, okay? So there's about to be another frame, 0.85% of a frame so far. If we're looking at audio, and we're doing audio at 1 millisecond packet time, then we divide it by this, and it's been that amount of audio samples since epoch, okay? So the key point here is that 2110 and AS67, they assume that everything started, including frames and samples, started at that time. So what that means? So it means that PTP is used by all devices to synchronize their local clock to the master clock. So we look at that. All my devices are synchronized to PTP. When we have that, we say that all these devices, they share a common clock. In our use of PTP, we synchronize all clock and frequency and phase, like we saw. I can adjust my time exactly. So everybody's device concept of time is the same, okay? Everybody knows exactly the same time and everything. The speed at which their clock moves is at the same. And what it means is I could have 2 devices that are measuring an input signal, and they will find it that exact same frequency. RTP timestamp, it's where it gets a little complicated, okay? So it might surprise you to know that RTP timestamp is not actually a timestamp in seconds. That would have been a little too simple, I think. So somebody decided that RTP timestamp were based on a 90 kilohertz clock. Okay, so what that means is that RTP timestamp, they increment by 90,000 every second. A tick of RTP is 11.111 microsecond. And so an RTP timestamp increments by 1800 every 20 milliseconds. So remember my 50 hertz signal? The RTP timestamp, every frame, it goes up by exactly 1800. Okay, so it's a frame's 20 milliseconds, divide by 11.111, you get 1800. This 90 kilohertz clock also started at epoch. Okay? So now there's a direct relationship between my RTP clock and my PTP clock because they all started at 0. Plus my frame, they all started at 0. That's part of how the 2110 specs works when it comes to RTP timestamp and clock. It's the same for audio, and it's the same for AS67, except audio uses a 48 kilohertz clock for a 48 kilohertz signal. If you have a 96 kilohertz signal, it's a little simpler. At least it's related this as opposed to 90 versus video. All right. Since the RTP clock starts at epoch, if I know the PTP clock value, I can figure out the RTP clock value. So when a frame of video comes into my baseband input on my converter, we record the PTP clock time when that VSync came in, okay? That frame of video is divided in multiple RTP packets, and then I figure out all the RTP packet will have the same RTP timestamp, that's the spec. And then the RTP timestamp we're going to use is going to be the one that matches that PTP clock we recorded when the frame came in. So in 2110 and AS67, all the frames and sample are aligned with the PTP clock that way. And we call that a synchronous signal. If we look a little bit what that looks like, I have this picture here where I have 25, okay, so 50 didn't fit on my page, so I use 25 frames per second here. So I have 25 frames per second media at the bottom. There's a square for every frame. And then I have two big black lines, and as you see, those black lines are aligned exactly with boundaries of frame. Between those two black lines, there's exactly 25 frames of media. There's exactly 90,000 ticks of RTP clock, and there's exactly 1 second of PTP clock. So our frames are aligned, they started at epoch, they match exactly, I'm several years after, and that VSync still aligns with that PTP clock at that number. That's a synchronized, sync, because everything's gen lock to house sync and everything. How do we use PTP in IPMX? So, like 2110, we use a 90 kilohertz clock because that's the spec. It's RFC 3550 spec that. We also assume that this 90 kilohertz clock starts at PTP epoch for some calculation. So when we start a new stream, we sample the PTP time for the VSync of our first frame, okay? It won't necessarily match the number that SMPTE uses because they're always aligned exactly to a boundary that's aligned to the PTP clock, but it'll be in the ballpark, right? It'll be within a frame, it'll be somewhere. So we take that value and we sample it. So just like 2110, we calculate what the RTP clock value would be that would correspond to this, and we use that value for the RTP timestamp of the first frame that we send out, only for the first frame. If I'm sending a signal that's 50 hertz, what I'm going to do after that is increment the RTP clock by that value, 1800, whatever it is. Why? The RFC 3550 says that's how that works. An RTP timestamp always increments by that number. There's, if you have 25 frames per second, doesn't matter if they're really slower or faster, your RTP timestamp are going to go up by 90,000 for your 25 frames of 25 frame per second video. Okay? So we set the clock for the first one, and after that, we increment by the number corresponding to the 90 kilohertz clock. So if our input signal is not perfectly 50 hertz, let's say it's 49.99999, we'll eventually drift with respect to what the RTP timestamp and frames would be for 2110. But we aligned it as close as we can. A synchronous video looks a little bit like this. Similar graphic than before. At the bottom I have my 25 frames of media and I put red lines at the, for the 25 frames. Between those two red lines there's exactly 25 frames of media. Between those 25 frames, because RFC 3550 says this is how it works, there's exactly 90,000 ticks of RTP timestamp. But there isn't exactly 1 second of PTP time, right? The 1 second of PTP time is a little bit wider for my design here, okay? So IPMX uses all the same concept, but the RTP timestamp and the RTP clock is not aligned perfectly with PTP time. It'll drift. It'll depend on if my signal is synchronous or not. That's where RTCP sender report come in. Like François explained to us, in an RTCP sender report, we have a PTP clock value that corresponds to the RTP time for our frame. Basically, every frame we say, by the way, because my RTP timestamp are perfectly aligned to PTP just like 2110, this is how they're aligned. I have my RTP timestamp for this frame corresponds to this time in PTP, this time. So remember when I did that first sampling of the RTP timestamp with the PTP clock and I put a number there? Well, now what I'm doing is I'm updating it every frame and saying, this is how it's aligned, this is how it's aligned, this is how it's aligned. And so we can compute the exact frequency of the input signal. The receiver can generate an output signal that matches that because both devices are locked to PTP. So if the input signal is actually synchronized, so if I take a signal that's gen-locked, an SDI signal that's gen-locked, and I feed it into my IPMX sender, right? And I do everything that I just explained to you, my signal at the output, my IPMX signal will be a synchronous signal. And it'll actually, my RTP timestamp will be perfectly aligned with the 2110 or AS67 RTP timestamp, and they won't drift. Because I went in and I took my sync and I measured the PTP clock time there, I generate the RTP, well, I did exactly what a 2110 device would do. The number is the same. And then I increment by the same number, and because everything is, at my input was locked, my output is locked. What's interesting to see also is that if we have what's called a synthetic sender, so a synthetic sender, for example, could be a piece of software reading a file from the hard drive, generating video frame, outputting them on the network, right? So if I'm locked to PTP, I'm gonna know, my notion of time is gonna be exactly the same notion of time of anything PTP and anything that is 2110, right? And so if my notion of time is that, and I'm trying to output 30 frames per second, I'm gonna output 30 frames exactly in 20 seconds, and therefore I'm really outputting my signal as a synchronous signal. My frames are gonna be aligned with PTP time and they won't drift. So if you have an IPMX device that's synthetic or a 2110 device that's synthetic, and there's PTP on the network for the IPMX device, and then the signal will be a 2110 signal. That's it. I hope I didn't lose you. Question?
Yeah, one question here.
Sure.
How do you know that the packets travel the same path of the network so that the delay signal is basically the same as the original signal of the sync, the first two PTP signals? Is there a mechanism that will guarantee that the packets will travel the exactly same path in a complex network, let's say?
No, there's no guarantee that they will travel exactly the same path, obviously. If the network decides to take different path, my packets will show up at different path, okay? And that will create a different jitter, I guess, on my packet, certain jitter, right? So in a IPMX device, just like other devices really that are dealing with streaming media, you usually design your device to be able to have like, to compensate for jitter, right? We call it de-jitter buffer, right? And so the spec of IPMX says how it works when you have a perfect network, you know? And then as an implementer of IPMX, I'm gonna add, you know, the de-jitter buffer into my device to deal with something. So maybe my device has a de-jitter buffer that I figured, I'm gonna have, I don't know, 1 millisecond for my de-jitter buffer, maybe 2 milliseconds for my de-jitter buffer. So when the packet comes in, I'm not gonna take them out exactly, you know, when it's at full, I'm gonna add an extra 2 milliseconds of buffering and then I'm gonna take it out. So now the packets come in, I extract them, but the timing and everything else is the same. Because remember, I'm timestamping at the sender saying this is when the packet came in. And the receiver looks at that. And it looks at the arrival time. And it can figure out at what speed. The goal is to consume the packet at the rate, the average rate they come in, so we don't starve and we don't overflow. And we're outputting, and we use this timing to consume at the right speed. But it's okay if you go like this and like this, as long as overall you have the same speed. We're trying to emulate an HDMI cable, basically. Yes?
That going side to side, the wander, is there any specification how much wander relative to a fixed reference is allowed?
So in the TR10 spec, it says how much jitter, maximum, the transmitter, so frame to frame, you should be there at this time and you know, not too much, you know, so you're allowed to go, I think the number is like 1 millisecond on either side. Like it's pretty big.
Okay. Yeah. I've seen problems in some 2110 systems with SDI wandering by plus or minus 30 microseconds, causing major knock-ons downstream.
Yeah, so that doesn't happen with IPMX. Those kind of number in microsecond, that's like, yeah, that's peanuts.
But you would therefore be happy with a device that has that relative wander in a device. Downstream system should be.
I won't be unhappy with it. They won't break me if that's what you're asking.
It's more about breaking the downstream SDI and HDMI systems.
So the downstream HDMI systems, right? I'm going to output the signal to the HDMI monitor with my local clock. I'm just going to get my local clock to be on average such that I can consume the packet without starving or anything. And you can move, you know, at a certain speed. And SDI is a lot more fragile to how much you move. But we do have devices, the implementation of IPMX that follow the spec that drive an SDI out signal without a problem over fairly you know, noisy, jittery, cheap switches system. Something where 2110 doesn't survive. Other question? All right, you up.